now I will start recording. So we are now, welcome, we are now on lesson number 10, I think. Yeah, me too. Me too. So we are in lesson number 10, and we are now starting slide number 6 on the multiplication rule. This lesson looks like, in terms of the number of slides, 15, which means it may be a one lesson section like the last two have been. I think the last two have been relatively easier than the ones that came before it, which is why I think some teachers, David's here just in time to start. Crazy talk. All right, so I think the syllabus for this class, because I haven't taught this in a number of years, I think the syllabus to this class is such that it's not really feasible to cover every single chapter. And I think some teachers skipped section 2, chapter 2, which was a higher level of difficulty than the ones that have come subsequently. And, you know, if I taught this class in the future, I would know to do that. But nevertheless, so let's start slide number 6, which is the multiplication rule. I'm going to share my screen, I think, and I learned yesterday something which I forgot, so I don't know how to do it. But apparently I can write on this and it will stay there. So hold on, I'm going to unshare for a second. And I'm going to go to Tools and Annotate, and I don't know if that's what yeah, okay, that's what I'm talking about. All right, so let's share the screen. And let's get started. So the multiplication rule. So it says the two categorical variables in this frequency table from the last lesson are independent. We saw that 6 over 10, 60%, 54 over 90, 60%, 4 over 10, 40%, 36 over 90, 40%. That we did last time. So it says change the table so that each cell contains the proportion of all girls who fall into that cell. This is the proportion of all girls, not some girls, okay? I don't want 6 over 10 here because I'm only focusing on princesses. I want 6 over 100 because I'm focusing on the total, 100. So for example, in this cell here, there's 6 over a total of 100. That's 6% or 0.06. How about this cell here? What would I put? Well, it's 4 over the total of 100. So what would I put?
4 over 100.
4 over 100. This is not the most conducive to writing. 4%. What would I put here?
54 over 9.
154.
Not over 90. It's always over 100.
Always over 100.
Right? We're doing over the total amount, over 100. So 54 over 100. And what would I put down here?
0.36.
0.36. Now, what do these two numbers add up to for the total over here?
0.60.
0.60. 60%. How about over here? Because this has to add to 1. What does this number have to be?
0.40.
0.40. And what's this over here?
0.90.
1.
0.90.
No. Oh, sorry.
And what's over here?
0.10.
0.10. Do we agree? And oh, look at you with the little cupboard there. Okay, so we have 6%, 4%, 54%, 36%, a total of 60% here, a total of 40% here, a total of 90% here, a total of 10% here, and of course overall it's 100%, which is 1.00. Okay, now suppose all you had were these numbers. Suppose you only had 0.6, 0.4, 0.9, and 0.1. Notice that they match here, 0.6, 0.4, 0.9, 0.1. Could you figure out a way, knowing that they are independent, can you figure out a way to put in numbers here, 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 and here So in other words, rather than having those numbers and getting the margins, we're going to start with the margins and we're going to get those numbers. So is there a way, knowing that they're independent, to go from the margins and figure out the 4 cells? Can anyone think of a way that might work? Let's think about this first one here. We know the actual answer is 0.06. So is there a way of using these numbers here in a logical and consistent way and ending up with 0.06 over here? So the answer is, take this number here, which is a total for that row, and this number here, which is the total for that column, and multiply them. What's 0.6 times 0.1?
6. No.
No. 0.6 times 0.1.
0.06.
0.06. Your calculator shall provide, which is the number that we had up here. Right?
Yes.
Okay. How about this note over here? Can we think of a consistent way to figure out what this one is? Now, we already know that, of course, these two have to add to 0.60, and as such, we know that this one has to be 0.54. But let's go through the same process. If I multiply this number here, which is the total for that row, times this number here, which is the total for that column, what is 0.6 times 0.9?
0.54.
0.54. And, okay, and what is 0.4 times 0.9?
0.36.
0.36. And what is 0.4 times 0.1?
0.04.
0.04. So knowing that they're independent allows us a method to actually compute the values inside the squares. If they weren't independent, I couldn't do that.
Just so I understand. So basically, all we have to do is multiply from the total to the part that to the other margin total in order for us to get the numbers in the middle.
If they're independent.
If they're independent. Okay.
If they're not independent, that will not work.
Okay.
Okay. So here's a frequency table for the boys. Now, it's a little different. I think this is a little sexist. The girls,
Yeah.
the boys get
Hello.
horses. I don't really.
2020.
I know, seriously. I mean, that's a really so archaic of a notion. I think it's horrible. But anyways, that's just me. So in this kingdom, there's also 100 boys, 10 princes, and 90 non-princes. They are the regular ones. 60 of them have horses and 40 of them do not have horses. Incredible. There's 2 princes that do not have horses. This is a crazy kingdom. Okay, this is nuts. The question is, are these values independent? Well, let's take a look. What is 60? Well, first of all, this is not a percentage, right? We got to first convert everything to percentages. We can't do 60 times 100. That makes no sense. But what we can do is we can replace everything with a percentage. What number would go here?
0.08.
0.08, 8 over 100. What goes here?
0.52.
0.52. What goes here?
0.02.
What goes here?
0.38.
0.38. And of course, these numbers add to
0.60.
0.60. And these numbers add to
0.40.
40, which they better because it has to add to 1. And what goes here?
790.
0.90.
90.
And what goes here?
0.10.
0.10.
0.10.
Is it, can that be 1 or it will be 10?
This one here?
Yeah. No. The total for the first row.
Well, it's 0.08 plus 0.02 is 0.10.
Map to 11, change writers. Change writers.
Someone infiltrating our class. No.
Who's in our class? Interesting. I don't know how to maximize this. See more people. Oh, I can do that. See more people. Hello. All right. So we have a spy. If we can figure out who the spy is, we'll deal with the spy accordingly. Anyways, the question is, if they were independent, what number should go here?
0.6.
0.6.
0.60.
0.06, no?
Oh, 06.
0.6 times 0.1, right? If
Oh.
they're independent, it'd be 0.06, correct? Yes?
Yes.
Yes.
What about this one here?
0.04. Oh, I'm sorry, you're reading the wrong way.
154.
54.54.
0.54. How about this one here?
0.04.
0.04. And how about this one here?
0.36.
0.36. Now, is that what we actually have?
No.
No, which means they're not independent. If they were independent, this is what we should have. Are they close to being independent?
Yes.
Yeah, they're fairly close to being independent, but they're not independent. Okay?
I have a question.
Yes.
I'm so sorry. I don't know if this is a dumb question or not, but I'm really confused on why the numbers have to do with the independency or not.
There are no dumb questions.
Thanks, Lori.
Well, I've heard some dumb questions in my life.
Oh.
Like,
I'm sorry. I'm confused.
like
None
what's
of
north?
them were from this class.
No, I didn't say that was a dumb question. I just said like, like what's north of the North Pole? Or are you full? These are just dumb questions, right? They just make no sense, right? Would you like some dessert? I mean, come on. I mean, what kind of question is that? That's just silly, right? That's just silly.
It's dumb.
But in this case, you're actually asking a very good question. Why exactly should independence imply this property? And you're right. We haven't really explained that. So it's not a dumb question at all. In fact, it's leading into what we're going to be doing next, which is why this rule should work for independence. Okay.
Okay, I also have a piggyback question, if that's okay.
A piggyback question.
Like going off of that question.
Oh, okay. Yeah, go ahead.
So if we say it's independent, that means they don't get affected by each other?
That means the occurrence of one does not change the likelihood of the other.
Okay.
Like for example, if I flip a coin and it's heads, is that going to change whether or not it's going to rain tomorrow?
No.
No, they're independent. The fact that one of them has occurred does nothing for the other.
Okay.
How does that apply in this case? Well, if I know that the person has a horse, does that change the likelihood of whether it's going to be a prince or a regular boy? Okay, does knowing that it's a horse affect the likelihood that it's a prince or a regular boy? Well, if it's a horse, according to this, right, we know that 6% of the princes have horses, correct? And 54% of regular are regular boys, right? Okay.
Yeah.
Now, if I didn't have that information at all, let me rephrase how I'm trying to say this. Suppose I want to calculate the probability that it's a horse. So, or better yet, let me try that again. The probability that it's a prince. Okay, if I pick someone at random, what is the probability that it's a prince?
50-50.
Not according to this. There's not
Oh.
50-50. How many princes are there? Go back to here.
Lost my thing.
How many princes are there?
10.
10. So what's the probability that it's a prince?
1 out of 10.
10 out of 100 or 10%, right? Correct? 10 out of 100?
Yeah.
Okay. Now, what's the probability that it's a prince given that the person is on a horse? So if we're on a horse, so if we go back here, if we know we're on a horse, then we're only dealing with these 60 people, right? We don't care about these 40. They're not part of the consideration, right?
Mm-hmm.
Because it's on a horse. There's 60 people on a horse. How many of those 60s are princes?
8.
8. So this would be 8 over 60, correct?
Yeah.
So that means that knowing that it's a horse has changed how likely it is that it's going to be a prince. Because before it was 10%, and now it's whatever this is not 10%.
Say that again, knowing that
Knowing that the person is sitting on a horse,
sitting on a horse.
right? Which I guess is what horse.
Oh, it
means, right?
changes.
It
okay.
changes how likely it is that the person is a prince. If I see someone from afar, if I just see someone standing there, it could be any one of the 100 people in the kingdom, right? Any of the 100 boys, right? And therefore, since 10 of the boys are princes, the likelihood that it's a prince is 10 out of 100. But if that person's on a horse, now all of a sudden the likelihood that it's a prince is 8 out of 60. It has changed how likely it is that the person is a prince.
So then this isn't independent.
This is not independent.
Okay, I got
because
it.
one
Thank you.
affects the other.
All right.
Had this number stayed the same, then who cares that it's a horse? It's still just as likely. And therefore, the occurrence of one does not affect the occurrence of the other. Okay, but this one here is not independent, and we see that by the fact that these numbers are not what we expect. If you did the same thing with these numbers, they would have been independent. Okay, so
I have a question.
yeah,
I have a question. Is that after 10 over 100, is that P parenthesis P1 1 minus 1, or is that like a dash to separate the
no,
P?
this is my amazing handwriting where I say the probability of a prince given that it's a horse.
Okay. Oh, it's an age. Never
Yeah,
mind.
I don't know how you missed that because it was so obvious, right? That is so clearly an H.
Okay, sorry.
Why don't you just use the pencil annotation rather than the marker annotation?
Because I'm having a lot of fun writing with these things, okay? And I want to have fun. Now, let's see, I have a text message.
You do you then.
Let's see what it says. You should submit your writing to Microsoft. Yes. What do you mean?
Like make your own font.
Oh my God.
It would be so legible.
I can have like, you can have like Cabrini, and then you can have like Berkey. I think it's amazing. I think that's perfect. We're gonna do this.
There's too many
And then,
choices.
like
as
King
far as I'm
David.
concerned.
King David. I've never heard that term before. That is so unique. Anyways, so the following rule works for each cell of the girls' table because the categorical variables are independent. It does not work for the boys' table because type of boy and horse ownership are not independent. So what is the multiplication rule for independent events? A and B are independent events if and only if this formula holds. If the probability of A and B is the product of the probability of A times the probability of B. This is why the rule works for the margin, for the table. Because the probability of A is that number in the total on the far right. The probability of B is the number in the bottom, total again. And if I multiply those two numbers, I get the probability of the intersection of those two, which is the square that we're looking for. This is why for independent events, total times total gives me the thing in the square. And I can do that for each and every square. If it's not independent, yeah, that's what I'm talking about. Right, Patty, go. If it's not in the, what is she doing? She's a little weird, this girl. Okay, if it's not independent, you can't do this. Okay. Oh my God, that is so cool. All right. Are you guys like sisters or something?
I think we were switched at birth.
I can see that because you definitely look like a Patty and she looks like an Angela.
Yeah.
That makes so much sense. Okay. Now,
Henry knows.
Henry knows they're magicians. They're magicians. That's right. Angela Copperfield. Oh my God, it's so cool. Okay, so, all right, let's go back. Suppose you pick a girl at random from those in the table. Use the marginal proportions and the multiplication rule for independent events to compute these probabilities. So again, we're going back, not to Prince, not to Prince, not to Prince, not to Prince. We're all the way back to, I guess, the very beginning.
What are they referring to, the marginal proportions? What does that mean?
Those are these values here, these totals when you look at probabilities instead of actual numbers. So this one here are actual numbers, right? Everyone follow my TikTok. I'm famous. I don't know what that means, but okay. So these numbers here 6, 54, 60, 6, 4, 36, 10, 90. These are the actual numbers, right? 6 actual princesses, 54 actual regular girls, and so on. These are the proportions. How many of them fall in here, or what percentage of them fall in here, and here, and here, and here, and here, and here, and so on. So keep these, maybe write them over again if we can keep them handy. We don't got to keep bouncing back and forth. I'm going to, I'll take a picture of them so I have it in front of me so I don't got to keep going back and forth.
Yeah, hold it. Don't move it yet because I didn't have my thing printed yet.
Okay, fine. Jeez.
Yeah.
My FYP can account for that. FYP, let me guess. I don't know what that means. Bet you don't have more than 60.
It's a For You page.
It's a what page?
A For You page.
For me? Oh, thank you. That's so sweet. Oh, that's amazing. Well, you know what? I teach 400 students, so I have 400 followers. What is that? Are you jogging? Is that a jogger? Why would anyone do that? Is someone chasing you? I don't understand. Okay, that just doesn't make any sense. All right, let's go back to the next one. All right, suppose you pick a girl at random from those on the table. So load up your table. I have mine right in front of me. It says use the marginal proportions and the multiplication rule for independent events to compute these probabilities.
Wait a minute.
I will wait 1 minute. 60 seconds, go now. Ooh, Raina does art. And I have 400 followers. 400.
Raina, you did not have to flex like that.
OMG. That's crazy. Is that a lot? Isn't there like people like the Kardashians have like millions of
I
followers?
have 27, so it's not that many.
27? Tell you what, I'll follow you. How's that? Now you'll have 28.
27 is better than nothing, though.
Right?
Wow. Wow, that hurts. She's stunning on these. What? I don't know what you guys...
Jose knows what's up.
I don't know what's going on right now. I just see weird things happening. All right. Professor, you are on TikTok. What does that mean? Did you just take a video of me and put it on TikTok? Oh, you're asking if I'm on TikTok? No, I'm not on TikTok. I don't even know what that is. I mean, I've heard of it, but I don't even know what it is.
Make one, you'd be famous.
Oh, would I? Would I be famous?
More famous than you already are.
I already have a very famous person with my name, so probably more famous than all of you put together. I don't know if you guys are familiar with my lineage.
Were you named after him?
Who am I named after? Why don't you go ahead and Google me, and you'll see who I was named after.
Never heard of
No,
him.
that's why I said, were you named after him?
Oh, actually, I wasn't. I was born in 1976, and he was made popular in 1977. So I beat him to the punch just a little bit. I'm sure if my parents would have known that was going to happen, they would have named me that anyway, but nevertheless. Okay. So.
Could be Bernie Madoff.
Bernie Madoff. Good man.
You could have been stuck with that.
Bernie? No. I would have changed my name. Okay. Yeah. So suppose you pick a girl at random from those on the table. Use the marginal proportions and the multiplication rule for independent events to compute these probabilities. We want the probability of being a regular girl and not wearing a crown.
Would it be the 36%?
Yes, it will be 36% because the square that pertains to regular girl not wearing crown, it's an and statement. So we want both of those to happen. And there's only one way both of those can happen, which is to be one of those 36 out of 100. Do we agree? We're still looking at all the 100 as the universe, as the consideration. Okay, and 36 of the 100 satisfy this property. How about a princess and not wearing a crown? How many of the 100 people, girls in the kingdom?
0.04 or 4 over 100.
4 over 100. Okay, 4 4 over 100. Do we agree? I got to get my kicks where I can find them. Okay, so let's go back to what we did a long time ago about area models. So area models, such as shown in the next example, are often used to help elementary and middle school students visualize the multiplication rule for independent events. Let's see how. Example. 3 out of 5 people sing in the shower. You want to find the probability that both your favorite actor and the CSUN president sing in the shower. I don't know who wrote this, but
Wouldn't that be 2 over 5?
no, it would not. Let's calculate it. On the area model on the next page, shade in the area that shows the event that both your favorite actor and the CSUN president sing in the shower. So let's take a look. Favorite actor, 3 sing, 2 do not. CSUN president, 3 sing, 2 does not. So I want my favorite actor and the CSUN president to sing in the shower. Right? Do we agree that those 9 squares represent the singing in the shower possibilities for both?
Yes.
And how many squares are there in total?
1, 2, 3, 4, 5.
36?
1, 2, 3,
How
4,
much?
5. No, 25.
25.
Oh,
so it
5.
should be 9 over 25, right? Now, does that make sense? Well, what's the probability that the CSUN president sings in the shower?
What? Doesn't?
Does what?
Can you please repeat the question?
What is the probability that the CSUN president sings in the shower?
3?
Probability.
Oh, I'm sorry.
3 over
Sings-
25.
No.
9. Sings in the shower.
The probability, what percent?
3 out of 25.
No, we're going to read the question. Read this.
9 a minute.
Read this.
6 out of 25.
How much?
6.
No, stop talking. No, look. I didn't mean that in a bad way.
It's okay.
3 out of 5 people sing in the shower. Right? This is the fact. 3 out of 5 people sing in the shower, correct?
Yes.
So any calculations we make about the likelihood of a random person singing in the shower comes from this. If 3 out of 5 people sing in the shower, then what percent, so what's the probability that a random person sings in the shower?
3 out of 5.
3 out of 5. So the CSUN president has a 3 out of 5 probability of singing in the shower. How about the favorite actor?
3 out of 5.
3 out of 5. Now, is there any connection between your favorite actor and the CSUN president?
Yes.
Really?
They sing the same amount of time?
No. It's not how much time they sing. The question is, what is, how do I do this? If whether or not you sing in the shower, is that connected to whether or not I sing in the shower?
No.
Or the next person sings in the shower?
No.
Or the next person sings in the shower. So whether or not the CSUN president sings is completely independent about whether or not your favorite actor sings. And as such, the likelihood that they both sing, according to the multiplication rule that we learned right here, is the likelihood that the first person sings times the likelihood that the second person sings. What is 3/5 times 3/5?
9 over 25.
9 over 25, which is where this number comes from. Because you singing or not singing is independent of whether I sing or not sing. Right? Now, if we interviewed siblings, if we interviewed people who live together, then perhaps, having the other person do it might affect whether or not you do it. But chances are that the CSUN president and your favorite actor do not live together. And as such, one singing or not singing has no effect on the other. They are independent events. Because they are independent, all I have to do is multiply their individual probabilities and I get the overall probability. And notice that the area diagram gives me exactly that. 9 out of the 25 squares are shaded. Does that make sense?
Yes, I have a question.
Yeah.
Yes.
The box that we didn't check, does that have a does that play any role into the equation?
Yeah, these 10 and those extra 16 is where the 25 comes from. We checked 9 and there's a total of 25.
Okay, I see.
So 9 over 25 is the probability, right? Ah, this is so annoying. There's got to be a easy way to do this. Okay. All right. With me? Okay, let's do another one. Read this example, please. Only because I have to drink something. Example. 70% of 18 to 34-year-olds shower for longer than 10 minutes, while only about 30% of people aged 55 and older shower that long. Suppose you pick an 18 to 34-year-old at random and a 55-plus-year-old at random. You want to find the probability that both shower for longer than 10 minutes. Okay? So first, do we understand the question?
Yes, it's asking us which age group showers the longest.
Doesn't say that actually. It says, I mean, we're told that 70% of 18 to 34-year-olds shower for longer than 10 minutes. Fact. 70% of them do. I don't know how they know this data, but 70% do. But only 30% of people aged 55 and older shower that long. Okay, these are both facts. These are not probabilities, these are facts. However, when you pick someone at random, you don't know whether or not they are amongst the 70% or amongst the 30%, right? We don't know, correct? It's a person at random. We want to calculate the probability that both shower for longer than 10 minutes. Now, if I pick two people at random, one between aged 18 to 34 and another who's 55 plus, are those two people independent of each other? Does whatever one do have any effect on whatever the other one does? No, right? So we're going to make an area model. We're going to make an area model. And your area model is probably better than mine. And we're going to divide it. Okay. I'm not going to do this on this because it's too hard. I'm going to stop sharing for a second and draw one out. So the area model is going to be a square, a big square, right? So let me stop sharing for a second. Okay, so here I have my big square. And I'm going to divide this into 10 rows and 10 columns. And in a perfect world, these would all be equally spaced.
You going? Rock.
Okay. So here we have a 10 by 10 grid. And on top, we're going to do the 18 to 34-year-old sings. And on the bottom is 50, on the side, I'm sorry, is 55 plus sings. So I label it like this.
Can you repeat that again? The side was what?
55 plus sings. Or does not.
Shower.
55 plus 6?
Sings.
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 It's shower, isn't it?
Huh?
Sings in the shower.
Sings in the shower. There's
No,
a
isn't it a 10-minute shower, not sings in the shower?
Oh, did I get that wrong?
Yes.
Oh,
Good call.
You're right. It's not sings. It's 18 to 34-year-olds.
Length of shower.
Yeah, takes long showers.
So 55 is length of shower.
They're both lengths of showers. I mixed up my questions. Takes,
And then the one across is
18 to 34-year-olds.
take long showers or 55
Long
plus
showers.
take long showers.
I'm sorry, Professor. I was distracted. That's 10 by 10 squares, right?
10 by 10. Unfortunately, this area diagram is really annoying because 70% is not a nice number. It would be nicer if they did like 25%. Then I could do 4 by 4, but they did 70%. 3, 4, 5, 6, 7. So actually, it's like this. Adapted a little bit. Okay, so because 70% take long showers, then the first 7 boxes should correspond to take long showers, and the last 3 boxes should correspond to do not take long showers. You see
so
what I
the
mean?
first 7 takes long showers.
And the last 3 is do not take long showers.
Is that not the same vertically as well?
Same vertically. 7 boxes are take long showers.
Did you do the bottom 7 or the top 7?
Wait, 1 second. Hold on. It makes no difference. For the 18 to 34-year-old, 70% take long showers. So you want 7 boxes for long showers and 3 boxes for short showers, right?
Yes.
For the 55 plus, only 30% take long showers. So you want 3 boxes for long showers. It doesn't make a difference where you put them, just 3 boxes for long showers. And the other 7 boxes does not take long showers. So I'm sorry if I was a little not exact in my original picture, but this one is better. So on top, there's 7 boxes for take long showers and 3 boxes for does not take long showers. And for the 55 plus, it's exactly the opposite. 3 boxes for long showers and 7 boxes for not long showers. Okay?
Wait a minute. Does not. Long showers.
Okay. So the question here is, it says, you want to find the probability that both shower longer than 10 minutes, that both take long showers. So I want you to shade in the squares that correspond to both taking long showers. I'm doing it with X's. Shade in the squares that correspond to both take long showers. And I'll give you a minute for that.
That bacon, my dog is looking at it like, I'm gonna eat that.
Okay, so you said shade in the ones that both take long showers.
Correct. So how many boxes correspond to both taking long showers?
21?
21. Out of how many boxes altogether?
Wait,
100.
100.
So what's the probability that they both take long showers?
21 over 100?
They 21 over 100. Right? 21 over 100, right?
Yes.
Okay. So does that match, if you look at slide number 9, does that match with the multiplication rule?
Show how to use multiplication.
The multiplication rule says if they're independent, which we think they are, all you have to do is multiply the individual probabilities. What's the probability that an old person takes a long shower?
30 out of 100.
Or 3 out of 10?
3 out of 10.
3 out of 10. And how about that a young person takes a long shower?
7 out of 10.
And if you multiply them, what do you get?
21 over 100.
That's just what this is indicating, right? The area model is just reinforcing visually the mathematical rule that when you multiply them, that's the answer.
I have a question. So how you got 7 out of 10 is because it says 7 boxes that it took for them to take a shower, right?
No.
7
out of 10 came from what I was given. Go back to the beginning of the example. 70% of 18 to 34-year-olds take long showers.
Can I see your graph again?
Yeah, I want to see your thing, your two.
70% is 7 out of the 10 boxes. If you divide 7 by 100, you're left with 3 boxes out of those first 10. So as you
Hold
go
on,
down,
I messed up my graph.
Professor?
Yeah.
You said that the area chart is a visual representation? Okay.
Yeah, the area chart is just a way of visualizing the multiplication rule. But when I teach this at a more advanced level, we don't do area models. We just do the math. But when you're teaching 3rd graders and 4th graders, then being able to see it in action really helps to make it stick.
Yes.
And for adults too, sometimes there's nothing wrong with people are visual learners, and they see when you see something visually, it can again be much better than just seeing some abstract mathematics.
so like when you're doing fractions, you draw that pie, and then you cut that pie in half, and you start showing them the different. Got it.
Same thing.
Okay, I understand where you got it from.
Congratulations.
But in this scenario, why'd you do 100 out of 100?
Because there's 100 boxes. Right?
Okay.
Of the 100 boxes, 21 of them were shaded, correct?
Yes.
So the likelihood of this event is 21 out of 100. That's the area diagram model, right? Number of boxes over total number of boxes. But
Okay.
I was able to get to a similar result mathematically by using the multiplication rule.
And you said 100 because 70 plus 30.
Well, just because if you look at the box, there's 100 boxes. 10 rows, 10 columns. That's 100 boxes.
Yeah, but from the example, we drew I mean,
Yeah, when you
10 by
draw
10.
this, you should get 100 boxes.
Right.
Of those 100 boxes, 21 of them are shaded.
Yeah.
So that's why it's 21 over 100.
Okay, I have a question. If it was 700 and 300%, would the boxes be 1,000?
Wait, what do you mean 700%?
Like, I want to know, how did you figure out that this has to be 100 boxes?
Oh, because 7%, or sorry, 70 and 30%. How many, okay, let's put it this way. If I had 2 rows and I shaded one of them, what percent would that be? 1 out of 2 is what?
1.
50%,
50%.
right?
50%, yes.
Okay. Can you get 70% using 2 rows?
No.
No. How about 3 rows?
No.
How about 4 rows? How about 5 rows? The smallest number of rows that you can generate 70% is 10. Because 7 out of 10 is 70%. But you can't get 70% from 9 or 8 or 7 or 6 or 5 or anything less than 10. It was the smallest number that I can get 70% for. Does that make sense?
Or you can think of it, 100 pennies make $1. That's what my last math professor. If you make it, sometimes kids understand money better.
Hey, I'm Jewish. That's how I understand things. So, and I can say
Yes,
I'm
you
Jewish. I can say that, by the way, just so you know. Okay, you can't say it, but I can say it.
Because it's easy to picture like 50 cents or 25
Sure,
cents.
sure. You focus on things that's why we use cards and dice and spinners, because these are things that kids and adults are familiar with.
Yeah.
Okay. So let's look now at, so let's go back to sharing my screen, and let's look now at this next example. You spin the spinner twice. What is the probability that it lands on yellow both times? Okay, well, first you have to ask yourself the following question. Are the 2 spins independent of each other? Does the first spin have any effect on the second spin? No, assuming that you hit it hard enough that it really makes no difference where you start, the 2 spins are completely independent, correct? Yes? No? Maybe so?
Yes.
Okay.
Yes.
Because of that, if I want to know the probability that it lands on yellow both times, I can just compute the probability that it lands on yellow the first time, and the same thing for the second time, and then just multiply them. So what is the probability that the first one lands on yellow? Look at the spinner, and tell me the probability that the first one lands on yellow.
1/6?
1/6, yeah.
Excellent, 1/6.
There's a takeover going on again.
Yeah. trying to figure out who that is. If you're not on mute and you're the one who has lots of noise in the background, please mute yourself. Thank you. Okay. Now, if it's a 1/6 probability that the first one lands on yellow, what's the probability that the second one lands on yellow?
1/6?
Also 1/6, right? They're both 1/6. So by the multiplication rule, what is the probability that they both land yellow?
1/6 or 1/36.
Ah, yes, 1 out of 36. Because if they're independent events, the probability that both of them occur is just the product of their individual probabilities. That is the multiplication rule.
How did you get 1/6? Sorry.
Because if you think of this as being like that,
6.
then the yellow is 1/6 of the entire thing. You agree?
Yes, thank you.
You're welcome.
So
Now,
that would be, I'm sorry, so that would be the probability of A times probability of B equals
yeah, so this is
probability of
A.
and B.
This is A, which is yellow on the, which is yellow
Yellow.
on the first flip. What the hell? That's A. That is B. And that is A. And B. What's the probability that it lands on red on the first one and blue on the second one?
1 out of 6 and 3 out of 6.
So what's the probability that it lands on red on the first one and blue on the second one?
1/2 on the blue.
And therefore, what's the probability that it lands yellow on the first and blue on the second?
1 out of 12.
1 out of 12. Because the two spinners are independent events. Because the two spinners are independent events, all you have to do is multiply their individual probabilities to get the probability of both.
Can you say that again, please?
Yes, the first spin and the second spin are independent, correct?
Yes.
So if I want the probability of both occurring, because they're independent, I just multiply their individual probabilities. The first one has a 1/6 probability. The second one has a 1/2 probability. And when I multiply them, I get 1/12. So if I was a betting man, which I am, and I said, I want to bet on red and then blue, mathematically, I know that the likelihood of that occurring is 1 out of 12, which means in the long run, that should happen every 12 times on average. Red then blue, red then blue, red then blue should occur every 12 times, which means I would want to structure my betting to account for that. But hopefully you're not a betting person because I lose a lot of money. Okay, you flip a coin and then you roll a die. Are flipping a coin and rolling a die independent events?
Yes.
Yeah.
Okay, so what's the probability that you get a head and a 6?
50-50.
1 second. A head and then a 6.
The head is
Oh.
1/2 and then a 6 is 1 out of 6.
And therefore, what's the probability?
1 out of 12.
1 out of 12. Because they're independent events, all you have to do is multiply their individual probabilities 1/2 times 1/6 to get the net probability 1/12. Does that make sense?
Yes.
Okay. And this applies for more than 2 events, right? As long as they're independent, you can extend it. A, B, and C. 3 events, just multiply each of their individual ones. So for example, you flip a coin, you roll a die, and then you roll 2 dice. 3 different events. And the question is, what is the probability to get a head, a 6, and then a sum of 5? So first event.
1 over 2.
1 out of 2.
1 out of 6.
And 5 out of 6.
I don't think it's
1 out of
5.
36.
1.
Sum of 5.
Oh, 2 out of 6.
I don't think it's 2 out of 6. First, how many outcomes are there? Always do denominator first. How many outcomes are there?
36.
36. Right?
How'd you
One
get
out-
36?
So 6 times 6.
Times
There's
6.
6 probabilities from one die. And
Oh,
6
yeah. I get that.
Now, how many ways are there of summing of 5?
4.
4. 1, 4, 2, 3, 3, 2, 4, 1. Right? So I would simplify first. 4 over 36 is 2 over 18. 2 over 18 is the same thing as 1 over 9. And then 6 times 9 is 54, times 2 is 108. So this is a very unlikely 1 over 108. Very unlikely 1 over 108. But it's the same rule, right? As long as they are independent events. Here's another one. You flip a coin 4 times. What is the probability that they are all heads? Are the 4 flips independent?
Yeah.
Yes.
Yeah, why does one flip affect the next one, right?
Yes.
So the first flip, what's the probability the first flip is a head?
1 over 4.
1/2.
1/2.
Oh,
2
1/2.
outcomes, right? Heads or tails? Right, Miriam?
Yes.
Second flip, heads.
1/2.
1/2. Third flip, heads.
1/2.
1/2. Fourth flip, heads.
1/2.
So what's the probability that they're all heads?
2,
1 out of
8.
16.
1 out of 16.
1 out of 16. Here's another one. If 50% of California students speak English at home, if you select 5 Californian students independently at random, what is the probability that they all speak English at home? Well, first, if you pick 5 at random, does any one of them speaking English have any effect on any of the other ones speaking English?
No.
No. Okay, if you pick 5 siblings, of course, it's very different. But they're at random, so chances are they're going to be all over the place. So what is the probability that they all speak English at home? Well, let's do the first one. What's the probability the first one speaks English at home?
57 over 100.
Or let's do the decimal 0.57. Agreed?
Okay.
How
Yes.
about the second one?
Same?
Same. Third one?
Same.
Same.
Same. Fourth one?
Same.
Fifth one?
Same.
So overall, it's going to be 0.57
Over 5? Not over 5. To the power of 5.
to the power of 5. And that's not something that you do in your head. So we get approximately 6%. Approximately 6%. Now, what's the probability that none of them speak English at home?
57%. 100%.
It's 100% that none of them speak English?
94%?
No guessing. No guessing. You got to
43%.
No, stop. No guessing. First of all, let me get the answer here so that if I hear it, I'll know it. No guessing. You got to give me a reason where your answer is coming from.
I got 0.94% because I subtracted the 0.6% from the 100. Nope. Okay.
43%? No.
So, first question. Are the 5 students that you're picking at random independent?
Yes.
Okay. So let's go to the first one. What's the probability the first one does not speak English at home?
43%.
43%. How about the second one?
Same.
43.
How about the third one?
Same.
Fourth one?
Same.
Fifth one?
Same.
So why isn't it just this?
How do you do that on this calculator, Professor? Sorry.
Which calculator?
The 84 plus the silver edition.
You do 0.43. And then you'll see a button on the right. A button on the right, which looks like an arrow like this.
Uh-huh.
Hit that.
Oh, okay. And then the 5.
And the 5.
And then enter.
Then enter.
Okay. Okay.
Make sense?
See.
See. That's yes in Hebrew. Okay.
Oui.
So then it says, often it's a judgment call as to whether events are independent and whether or not you can use the multiplication rule. Okay? Because you're only allowed to use the multiplication rule if they're independent. If not, you can't do it. So here's an activity. A driver was cited for overtime parking in a 1-hour zone. The parking officer had come by and recorded the valve stems on the left side tires were at 1 and 6. When he came back over an hour later, the valve stems were still at 1 and 6. The driver claimed he had left and returned. Do you rule guilty or not guilty? Guilty or not guilty? So the question you have to ask yourself is, how likely is it that the first time he was there, the valves ended here and here, and the second time they ended in exactly the same spot? Okay? If you believe that that is a possibility or a likely possibility, then you can say, okay, maybe he's telling you the truth. If you believe that that is a very unlikely possibility, then you say he's not telling the truth, right? Do you rule? So what would you do in that situation? Would you say you're full of it, or would you say, okay, fine, I'll give you the benefit of the doubt?
I'm pretty sure he never moved.
Yeah, I mean, if you think about it, a full circle has essentially 360 degrees, correct? So when the valves end at a certain location, it's essentially, the pair of them have 180 possibilities, because once they overlap, it's only half a circle. After that, it's the same again. So you're basically saying that there's a 1 in 180 chance that they ended in exactly the same spot. 1 in 180 is it's about 0.5%. So personally, I think he's full of shit. That's just my personal opinion, and we should throw the book at him and he should go to jail forever. That's just my first inclination.
We're parking in the wrong line.
What was that?
Except for.
Oh man, you went silent just by your punchline.
Oh, I forget it.
No, now I want to know what you said. That's horrible. What a horrible time to go, oh my God, it's like God are telling you shouldn't be talking. Wow, that's just horrendous. Anyway, quickly, what if events are not independent? Well, unfortunately, we're not going to have time to do this. We only have 3 minutes left of class. So we didn't quite finish the last 2 slides. We will finish them on Tuesday. And again, the exam is scheduled for this coming weekend. Oh, I got some people sending me texts. Hold on. I'm depressed. Why are you depressed? Oh, because class is coming to an end? Oh. No, I did like this, and then like that, right? Okay. I did like love IU. I'm not dyslexic. That doesn't make any sense. So this, that. That's how I should have done it. But anyways, go eat. I never stop, man. I never stop. Anyway, so what is that? Yeah, that's good. Anyways, I will put the quiz up for chapter 3. I'll put it up probably tomorrow because I'm too lazy to do it today. And you'll have the weekend to do it. Just do it when you'll get around to it. It'll be labeled as quiz number 2. And then we will finish this chapter 6, early on Tuesday. And we're also going to have a quiz on chapter 4 next week because we have to have more quizzes. We're kind of falling behind. So there'll be a quiz on 3 and then a quiz on 4 and then the exam on the first 6 chapters. First 6 chapters are kind of like a nice break conceptually, but we will start chapter 7 on Tuesday as well. Wow, I know. I'm not sure what you're wowing though. I mean, you could be wowing me, in which case, thank you. But you could be wowing something else, in which case, what? I'm in charge here. Focus on me. So it can really go in both directions. But that being said, are you putting the quiz on your assignments? Yeah, the file. I put everything on files. So it'll be labeled quiz 2. You should be able to find it.
I have a question.
Yes.
How many problems are going to be on the test?
Probably 100, maybe 200. If that's too much, maybe like 10. I don't know. I haven't decided yet. But 5, 10. I don't know. It'll be somewhere between 1 and 1 million. I can promise you that. Probably closer to 1 than 1 million. But it'll be 2 hours. No, it's not 2 hours. It's an hour, 15-minute class. It'll be an hour, 15 minutes, and it will be doable in an hour, 15 minutes. Okay. No surprises. The questions will be similar to things that you've seen before. Either the homeworks or things that we did in class. Okay. So I'm going to go take a break. I'm going to stop recording now.